Imagine you're a brilliant mathematician. You've spent 25 years of your life building what you believe is the perfect logical foundation for all of mathematics. Your masterwork is finally going to print, and then you receive a letter. 2 pages that will destroy everything you've worked for and shake the very foundations of mathematical truth itself. This isn't fiction. This is the true story of how a simple question about sets that don't contain themselves nearly brought down the entire structure of mathematics. Welcome to the story of Russell's paradox, a contradiction so profound that it forced mathematicians to rebuild their subject from the ground up. Let's begin our story in the late 1800s, at a time when mathematics seemed to be approaching perfection. Picture the intellectual landscape of Europe in 1890. The Industrial Revolution was transforming society. What an equally dramatic revolution was happening in the world of pure thought. Mathematics was experiencing what many considered a golden age. Mathematicians had conquered problems that had puzzled humanity for thousands of years. They developed rigorous foundations for calculus, eliminating Berkeley's famous criticism about ghosts of departed quantities. They discovered non-Euclidean geometries, shattering the 2,000-year belief that Euclidean geometry represented absolute truth about space. And perhaps most remarkably, Georg Cantor had opened up entirely new realms of mathematical reality with his theory of infinite sets. David Hilbert, one of the greatest mathematicians of all time, captured the optimism of the era when he declared, "No one will cast us out from the paradise that Cantor has created for us." But paradise, as we know from older stories, can harbor serpents. At the center of our story is a man whose name you might not recognize, but whose work transformed human thought forever. Gottlob Frege was born in 1848 in the small German town of Wismar. He would spend his entire career at the Provincial University of Jena, slowly climbing the academic ladder while working on ideas so revolutionary that his contemporaries couldn't understand them. Frege was a man possessed by a single, magnificent obsession: the idea that mathematics could be reduced to pure logic. He believed that numbers, equations, theorems, all of mathematics, were really just elaborations of logical truth. This wasn't just an academic curiosity. Frege was attempting to secure the absolute certainty of mathematical knowledge by grounding it in the laws of pure thought itself. To pursue this vision, Frege essentially invented modern mathematical logic. In 1879, he published a work called Begriffsschrift Konzeptschrift that introduced the world to quantificational logic, the foundation of all modern logical reasoning. He developed new ways of analyzing mathematical statements that were centuries ahead of their time. But Frege's crowning achievement was to come later: his Grundgesetz der Arithmetik, the basic laws of arithmetic. This was meant to be the complete reduction of mathematics to logic, worked out in painstaking detail over 2 massive volumes. The first appeared in 1893. The second was nearing completion as the new century dawned. Frege was not an easy man to know. Colleagues described him as introverted and increasingly bitter about the lack of recognition for his revolutionary work. He had what one biographer called a vivid awareness of his own genius and a belief that it would one day be recognized. But recognition wasn't coming. His first book received only 1 review, a devastating critique from Georg Cantor, who completely missed the point of what Frege was trying to accomplish. Yet Frege persevered, sustained by his absolute faith in logical truth. He was creating what he believed would be the unshakable foundation for all human mathematical knowledge. He had no idea that a young English aristocrat was about to bring it all crashing down. Enter Bertrand Russell, 29 years old, in the spring of 1901. Russell was everything Frege was not: aristocratic, well-connected, confident, and ambitious. Born into British nobility as the grandson of Lord John Russell, a former Prime Minister, Bertrand had received the finest education available. He'd studied mathematics at Trinity College, Cambridge, and had already made a name for himself in both mathematics and philosophy. But Russell was restless. He was searching for absolute certainty in human knowledge, and he believed mathematics held the key. Like Frege, Russell was convinced that mathematics could be reduced to pure logic, what philosophers call logicism. But Russell was approaching the problem from a different direction. In 1900, Russell attended the First International Congress of Philosophy in Paris, where he encountered the work of Giuseppe Peano, the Italian mathematician who had developed precise logical notation for mathematics. This encounter was a revelation. Russell later wrote that learning Peano's methods gave him precision of thought that he had never achieved before. Returning to Cambridge, Russell threw himself into the project of grounding mathematics in logic. He was working on what would become the principles of mathematics, and he was making rapid progress. Russell was young, brilliant, and confident. He believed he was on the verge of solving one of philosophy's greatest problems. But in May of 1901, Russell was studying Georg Cantor's famous proof that there is no greatest cardinal number, no largest possible size of infinity. As Russell later recounted, he was trying to understand Cantor's diagonal argument when he stumbled upon something strange. Let me take you inside Russell's mind during those crucial days in the spring of 1901. Russell was working with the concept of sets, collections of objects. In those days, mathematicians worked with what we now call naive set theory. The basic principle seemed innocent enough. For any property you can define, there exists a set containing exactly those objects that have that property. So there's a set of all red things, a set of all even numbers, a set of all triangles, and so on. This principle, called unrestricted comprehension, seemed obviously true. How could it not be? Russell was particularly interested in very large sets. He was thinking about the universal set, the set containing absolutely everything. Since this set contained everything, it would contain all other sets as elements. It would even contain itself. Now, most sets don't contain themselves. The set of all cats doesn't contain itself because the set itself isn't a cat. The set of all even numbers doesn't contain itself because a set isn't a number. This seems normal, but some sets might contain themselves. The set of all abstract objects, for instance, is itself an abstract object, so it would contain itself. The set of all things mentioned in this video would contain itself because we just mentioned it. So far, so good. Sets can be divided into two types, those that contain themselves and those that don't. Here's where Russell made his devastating observation. Russell considered the set of all sets that do not contain themselves. Let's call this set R now. Russell asked himself a simple question. Does R contain itself? Think about this carefully. If R contains itself, then R is a member of the set of all sets that don't contain themselves. But that means R doesn't contain itself. Contradiction. On the other hand, if R doesn't contain itself, then R belongs to the category of sets that don't contain themselves. But R is precisely the set containing all such sets. So R must contain itself. Contradiction again. Either way, we get a contradiction. This was Russell's paradox. Russell immediately grasped that this wasn't just a clever puzzle. This was a fundamental logical contradiction at the heart of set theory. And since mathematics was increasingly being understood in terms of sets, this threatened the foundations of all mathematical knowledge. But Russell knew he wasn't the first person to think carefully about these issues. There was one man, above all others, who had devoted his life to building mathematics on logical foundations: Gottlob Frege. Russell realized he had to tell Frege about his discovery. What he didn't know was the devastating timing of what he was about to do. Picture Frege in the spring of 1902 as the second volume of his Grundgesetz was going through the final stages of printing. At 54, Frege had devoted over 2 decades to this project. He was finally about to complete his life's work: the complete reduction of arithmetic to pure logic. The first volume, published in 1893, had laid out his logical system in meticulous detail. The second volume would demonstrate how all of arithmetic could be derived from these purely logical principles. It would be his vindication, his proof that mathematics was nothing more than an extension of logic itself. The printing was nearly finished. Frege was probably already imagining the day when his work would finally receive the recognition it deserved. And then, on June 16, 1902, the letter arrived. Russell began politely. He had great admiration for Frege's work, he said. He had studied Frege's system carefully and found it brilliant. But there was just one point where Russell had encountered a difficulty. With characteristic English understatement, Russell was about to destroy 25 years of work. Russell explained his discovery with mathematical precision. Let W be the predicate of being a predicate that cannot be predicated of itself. Can W be predicated of itself? From either answer follows its contradictory. We must therefore conclude that W is not a predicate. Likewise, there is no class as a whole of those classes which, as wholes, are not members of themselves. Then came the devastating conclusion. From this, I conclude that under certain circumstances, a definable set does not form a whole. This was the end of unrestricted comprehension. This was the end of Frege's system. This was potentially the end of the logical foundations of mathematics. Imagine Frege reading this letter. Years later, Russell would describe what happened next as almost superhuman in its intellectual integrity. Frege responded just 6 days later, on June 22, 1902. His response reveals both his mathematical brilliance and his deep personal anguish. Your discovery of the contradiction caused me the greatest surprise and, I would almost say, consternation, since it has shaken the basis on which I intended to build arithmetic. Frege immediately saw that Russell had found a fatal flaw in his system. Basic Law 5, the principle that had allowed Frege to move from concepts to sets, was inconsistent. But Frege didn't deny the problem or dismiss it. Instead, he wrote with heartbreaking honesty, "Hardly anything more unwelcome can befall a scientific writer than that one of the foundations of his edifice should be shaken after the work is finished." Now, you might be thinking, this is just a philosophical word game. Who cares about sets that contain themselves? How does this threaten mathematics? This reaction is understandable, but it misses the profound implications of Russell's discovery. Let me explain why this paradox struck at the very heart of mathematical reasoning. To understand the stakes, we need to understand what was happening to mathematics in the late 19th century. Mathematicians were realizing that almost all of mathematics could be expressed in terms of sets. Numbers could be defined as sets. Functions could be understood as sets of ordered pairs. Geometric objects could be represented as sets of points. Even logical operations could be modeled using set theory. If set theory was inconsistent, if it contained contradictions like Russell's paradox, then all of mathematics was potentially inconsistent. And from a contradiction, anything can be proven. In classical logic, if you can prove both P and not P, then you can prove any statement whatsoever. Mathematicians call this the principle of explosion. Think about what this meant. If Russell's paradox showed that set theory was inconsistent, then you could potentially prove that 2 plus 2 equals 5, that parallel lines meet, that there are no prime numbers, or any other false statement you wanted. The entire structure of mathematical truth would collapse. But let me give you a more intuitive sense of why the paradox is so troubling by presenting it in a different way. Russell himself later popularized this version, though he warned it wasn't a perfect analogy. Imagine a town with exactly one barber. This barber has a very specific job. He shaves all and only those men in the town who do not shave themselves. Now, here's the question. Does the barber shave himself? If the barber shaves himself, then he's someone who shaves himself, which means he should not be shaved by the barber. But he is the barber. Contradiction. If the barber doesn't shave himself, then he's someone who doesn't shave himself, which means he should be shaved by the barber. And he is the barber, so he should shave himself. Contradiction. The barber paradox captures the same logical structure as Russell's paradox, but in a more everyday context. And just like Russell's paradox, It shows that our seemingly reasonable definitions can lead us into impossible situations. Here's another way to think about it. Imagine you're organizing your personal library, and you decide to create catalogs for different categories of books. You might have a catalog of all fiction books, a catalog of all science books, a catalog of all biographies, and so on. Now, some of these catalogs might be listed in themselves. The catalog of all books in your library would presumably list itself, since it is a book in your library. But most catalogs wouldn't list themselves. The catalog of fiction books isn't itself a work of fiction. So you decide to create a special catalog, the catalog of all catalogs that don't list themselves. This seems like a perfectly reasonable thing to do. But now ask yourself, should this special catalog list itself? If it lists itself, then it's a catalog that lists itself. So it shouldn't be in the catalog of catalogs that don't list themselves. But if it doesn't list itself, then it's a catalog that doesn't list itself. So it should be listed in the catalog of catalogs that don't list themselves, which is itself. This is Russell's paradox in action, and it shows how quickly our intuitive reasoning can lead us into contradiction. Back to our historical drama. Frege's response to Russell was swift and comprehensive, but the damage was irreparable. Frege immediately began working on a solution. He tried to modify his system, weakening some of his logical principles to avoid the contradiction. But his proposed fixes created new problems, and he was never able to restore the full power of his original system. In a hastily written appendix to the second volume of Grundge's sets, Frege acknowledged the problem and attempted a partial solution. But the appendix reads like a brilliant mind in crisis, grappling with the collapse of everything he had worked for. The impact on Frege was devastating. This man, who had essentially invented modern logic, would develop the conceptual foundations that still underlie contemporary mathematics and computer science, produced virtually no significant work for the next 7 years. His later writings show increasing bitterness and disillusionment. Russell, meanwhile, immediately threw himself into finding a solution. He was young, optimistic, and confident that the problem could be solved. He began developing what would become known as the theory of types, a hierarchical approach designed to prevent the self-referential constructions that led to paradox. But Russell wasn't the only one grappling with these issues. Word of the paradox spread quickly through the mathematical community. Ernst Zermelo, a German mathematician, had actually discovered similar contradictions independently around the same time, but he hadn't publicized them. The foundational crisis was deepening. It wasn't just Russell's paradox. Other paradoxes were emerging from the seemingly solid foundations of set theory and logic. There was the Burali-Forti paradox involving ordinal numbers, Cantor's own paradox about the set of all sets, and various semantic paradoxes involving language and truth. David Hilbert, the great German mathematician who had spoken so optimistically about Cantor's paradise, began to realize that more drastic measures were needed. The informal methods that mathematicians had used for centuries weren't sufficient for the new levels of abstract reasoning that mathematics was reaching. Russell's first response to the paradox was characteristically ambitious. He would solve it by rebuilding the foundations of logic itself. Working with his former teacher, Alfred North Whitehead, Russell embarked on one of the most monumental projects in the history of mathematics. The result was the theory of types, first outlined in Russell's 1903 Principles of Mathematics, and then developed in exhaustive detail in the 3-volume Principia Mathematica, published between 1910 and 1913. Russell's key insight was that the paradoxes arose from a kind of logical mixing of types, treating objects of different logical categories as if they belonged to the same category. His solution was to impose a strict hierarchy on mathematical objects. Here's how it worked. At the bottom level, Type 0, you have individuals, concrete objects like people, chairs, numbers. At Type 1, you have sets of individuals, collections of concrete objects. At Type 2, you have sets of individuals. At Type 3, you have sets of individuals. and so on, climbing an infinite hierarchy. The crucial rule was that membership statements were only allowed between consecutive types. An object of type n could only be a member of a set of type n plus 1. This prevented the self-referential constructions that led to paradox. Russell's set R, the set of all sets that don't contain themselves, simply couldn't be formulated in this system. To ask whether a set contains itself, you'd need the set and its potential member to be of the same type, but the membership relation only works between different types. The theory of types was mathematically rigorous and logically sound. It avoided the known paradoxes and allowed for the development of mathematics within a consistent framework. Russell and Whitehead used it to derive much of mathematics from purely logical principles, seemingly vindicating the logicist program. But the system had serious drawbacks. It was incredibly complex, requiring elaborate notation and cumbersome restrictions. More fundamentally, it seemed to multiply mathematical objects unnecessarily. In Russell's system, there wasn't just one empty set. There was an empty set at each type level. There wasn't just one number 2. There were infinitely many versions of 2, one at each type level. To make the system work for ordinary mathematics, Russell and Whitehead had to introduce the axiom of reducibility, which essentially collapsed the type distinctions for mathematical purposes. But this axiom seemed ad hoc and unmotivated, undermining the elegant simplicity that had motivated the logicist program in the first place. Many mathematicians found Russell's system too complicated and artificial for practical use. Solve the paradox, but at what seemed like an excessive cost in complexity and naturalness. As Russell was developing his type theory, other mathematicians were pursuing different approaches to the foundational crisis. The most influential alternative came from Ernst Zermelo, who proposed a radical solution. Instead of modifying logic, why not modify set theory itself? In 1908, Zermelo published a paper that would transform mathematics. Untersuchungen über die Grundlagen der Mengenlehre, Investigations in the Foundations of Set Theory. Instead of allowing unlimited set formation, Zermelo proposed a specific list of axioms that would determine exactly which sets could exist. Zermelo's key insight was to replace the unrestricted comprehension principle, the idea that any property defines a set with a much more limited principle called separation or specification. Instead of saying for any property P, there exists a set containing all objects with property P, Zermelo said. For any property P and any existing set A, there exists a subset of A containing exactly those elements of A that have property P. This might seem like a small change, but it was revolutionary. It meant that you could only form new sets by taking subsets of existing sets. There was no way to form the universal set containing everything, and therefore no way to construct Russell's paradoxical set. Zermelo's approach was later refined and extended by Abraham Fraenkel, Thoralf Skolem, and others. The result, known as Zermelo-Fraenkel set theory with the axiom of choice, or ZFC for short, became the standard foundation for mathematics. ZFC solved Russell's paradox elegantly. The Russell set R simply doesn't exist in ZFC. You can prove this directly. Suppose, for the sake of argument, that there exists a set R containing exactly those sets that don't contain themselves. Then by Russell's reasoning, R both does and doesn't contain itself. A contradiction, since we assume ZFC is consistent, R cannot exist. But ZFC represented a significant philosophical shift. Instead of trying to capture our intuitive notion of set, the idea that any well-defined collection should form a set, it accepted that this intuitive notion led to contradictions and replaced it with a more restrictive axiomatic system. In ZFC, sets are built up in a cumulative hierarchy. You start with the empty set, then form all possible sets that can be built from the empty set, then all possible sets that can be built from those sets, and so on. This gives you a well-ordered, well-founded universe of sets that avoids the paradoxes but still supports all of classical mathematics. The ZFC approach was pragmatic and successful. It provided a consistent foundation for virtually all of mathematics, and it remains the standard foundation today. But it came at a cost. It abandoned the ambitious project of reducing mathematics to logic alone. Set theory, as axiomatized in ZFC, was recognized as a mathematical theory in its own right, not a branch of pure logic. While Russell and Zermelo were developing their systematic approaches, other mathematicians proposed more radical solutions to the foundational crisis. The Dutch mathematician Lee J. Brouwer founded a school called intuitionism, which proposed solving the paradoxes by changing mathematics itself. Brouwer argued that mathematics should be based only on mental constructions that could be carried out in finite time. He rejected the law of excluded middle, the principle that every statement is either true or false when applied to infinite collections. From an intuitionist perspective, Russell's paradox wasn't a real problem because the infinite totalities involved in the paradox couldn't be constructed. Brouwer's approach avoided the paradoxes, but it required abandoning large portions of classical mathematics, including much of analysis and set theory. David Hilbert took yet another approach. Initially, Hilbert had been optimistic about set theory, famously declaring that no one shall expel us from the paradise that Cantor has created. But as the paradoxes multiplied, Hilbert realized that more drastic measures were needed. Hilbert proposed what became known as his formalist program. Mathematics, Hilbert argued, should be viewed as a formal game played with meaningless symbols according to precise rules. The meaning of mathematical statements was less important than their consistency, their freedom from contradiction. Hilbert's program aimed to prove the consistency of mathematics using only finitary methods, methods that could be carried out in finite time and involved only concrete mathematical objects. If successful, this would show that mathematics was safe from contradiction, even if we didn't fully understand what mathematical statements meant. Another intriguing approach came from the American logician Willard Van Orman Quine. In 1937, Quine proposed a system called new foundations that allowed a universal set while still avoiding Russell's paradox. Quine's key idea was stratification. In new foundations, you can form the set of all objects satisfying a property, but only if that property can be expressed in a stratified way, roughly, a way that respects type distinctions, even though the system doesn't explicitly have types. The formula X is not a member of X cannot be stratified because both occurrences of the variable X would need to be at the same type level. Therefore, Russell's set cannot be formed in new foundations. But other large sets that are impossible in ZFC, including a universal set, are allowed. New foundations is a fascinating system that proves many surprising theorems. For instance, it disproves the axiom of choice and proves the existence of infinite sets as a trivial consequence of its axioms. For many years, mathematicians weren't even sure if new foundations was consistent, but recent work has finally established its consistency. As mathematicians grappled with Russell's paradox and related foundational issues, the implications spread far beyond the technical details of set theory and logic. The paradox had revealed something profound about the nature of mathematical reasoning itself. First, it showed that our intuitive understanding of mathematical concepts could be deeply flawed. The principle of unrestricted comprehension, the idea that any property defines a set, had seemed obviously true to most mathematicians, yet it led directly to contradiction. This was a humbling discovery. It suggested that mathematical intuition, while valuable, was not infallible. The great mathematical structure that had been built over centuries was not as secure as its builders had believed. Second, the paradox highlighted the subtle dangers of self-reference. Russell's paradox, the liar paradox. This statement is false, and many other logical puzzles all involve statements or constructions that refer to themselves in some way. The paradoxes suggested that self-reference was a source of logical instability that needed to be carefully controlled. This insight has had lasting influence beyond mathematics. In the 1930s, Kurt Gödel would use similar self-referential constructions to prove his famous incompleteness theorems. showing that any sufficiently powerful mathematical system must be either incomplete or inconsistent. The techniques Gödel used were directly inspired by the logical methods developed to understand Russell's paradox. The paradox also had profound implications for philosophy. Since the time of Plato, philosophers had often viewed mathematics as a realm of perfect, eternal truth. Mathematical objects like numbers and geometric figures seem to exist in a timeless mathematical reality, and mathematical truths seem to be absolute and unchanging. But Russell's paradox suggested that this Platonic picture was too simple. Our basic concepts of mathematical objects led to contradictions. What did this say about the nature of mathematical reality? Were there really mathematical objects out there waiting to be discovered? Or were mathematical truths more dependent on the particular axiom systems we chose to adopt? Different schools of mathematical philosophy gave different answers to these questions. Formalists like Hilbert emphasized the formal, game-like aspects of mathematics. Intuitionists like Brewer emphasized the constructive, mental aspects. Platonists argued that mathematical objects still existed objectively, but that our access to them was more limited than previously thought. These debates continue today. Modern mathematics has largely adopted the pragmatic approach embodied in ZFC set theory, a system that avoids the known paradoxes and supports the mathematics that practicing mathematicians want to do. But the deeper philosophical questions raised by Russell's paradox remain unresolved. The story of Russell's paradox doesn't end with its resolution in the early 20th century. The paradox continued to influence mathematical thinking throughout the century, culminating in some of the most important discoveries in the history of logic. In 1931, Gödel published 2 papers that would forever change our understanding of mathematical systems. His incompleteness theorems showed that any mathematical system powerful enough to express basic arithmetic must be either incomplete, unable to prove all true statements, or inconsistent, able to prove contradictions. Gödel's proof used a technique that was directly inspired by Russell's paradox and other self-referential constructions. Gödel essentially constructed a mathematical statement that said, about itself, I cannot be proven in this system. This created a paradox-like situation. If the statement can be proven, then it's false, since it claims it can't be proven. But if it can't be proven, then it's true, and we have a true statement that the system can't prove. Gödel's work showed that the foundational problems raised by Russell's paradox went even deeper than mathematicians had realized. It wasn't just that naive set theory was inconsistent. It was that any sufficiently powerful mathematical system would have fundamental limitations. This was a shocking discovery. Hilbert's program, the attempt to prove the consistency of mathematics using finitary methods, was shown to be impossible. Mathematics could not provide its own ultimate guarantee of consistency. Recent research has revealed even deeper connections between Russell's paradox and Gödel's theorems. The same principle that generates Russell's paradox. This means that Russell's discovery didn't just reveal a problem with naive set theory. It pointed toward fundamental limits in the very nature of mathematical reasoning. The self-referential constructions that create Russell's paradox are closely related to the self-referential constructions that Gödel used to prove his incompleteness theorems. These connections extend beyond pure mathematics. In computer science, Russell's paradox has influenced the development of type systems in programming languages. Modern languages like Haskell, Scala, and Rust use sophisticated type hierarchies that prevent many of the logical errors that can occur with unrestricted self-reference. The paradox has also influenced work in artificial intelligence and cognitive science. Researchers studying how humans and machines reason about self-reference and recursion often draw on the insights first developed to understand Russell's paradox. One of the most remarkable aspects of Russell's paradox is how it has transcended its technical mathematical origins to become part of popular culture. The Barber paradox version that Russell popularized has appeared in countless logic puzzles, philosophy textbooks, and even works of fiction. The paradox appears in Douglas Hofstadter's Gödel, Escher, Batch, one of the most successful popular books about mathematics and logic ever written. Hofstadter uses the paradox as an entry point for exploring deep questions about self-reference, consciousness, and artificial intelligence. Television shows have referenced the paradox as well. The classic Star Trek episode, Mudd features an android that is disabled by being presented with a version of the liar paradox. While this is scientifically implausible, it reflects a popular understanding that self-referential paradoxes pose fundamental challenges to rational systems. In educational settings, Russell's paradox serves as a powerful example of how mathematical reasoning can lead to surprising conclusions. It's often used to introduce students to the importance of careful definition and logical precision in mathematics. The paradox also illustrates broader themes about the nature of knowledge and certainty. Students often find it unsettling that such a simple question, does the set of all sets that don't contain themselves contain itself, can lead to contradiction. This discomfort is valuable. It helps students appreciate that mathematical reasoning, while powerful, must be approached with care and humility. Many mathematics educators use the paradox to introduce students to different approaches to mathematical foundations. By comparing Russell's type theory with Zermelo's axiomatic approach, students can see how the same mathematical content can be organized in very different ways. The paradox also provides a historical entry point for discussing the development of modern mathematics. Students can follow the human drama of the Russell-Frege correspondence and see how mathematical crises can lead to new insights and approaches. You might think that Russell's paradox, discovered over 120 years ago, would be of purely historical interest today. After all, we have ZFC's set theory, which provides consistent foundations for mathematics. The paradox has been solved, so why do mathematicians and philosophers continue to study it? The answer is that Russell's paradox continues to generate new insights and research directions. In recent decades, there has been what the Stanford Encyclopedia of Philosophy calls an explosion of interest in Russell's paradox among researchers in mathematical logic and philosophical studies. One active area of research involves plural quantification approaches. Instead of talking about sets, some logicians propose understanding Russell's paradox in terms of quantification over pluralities, multiple objects considered together without forming a set. This approach, developed by researchers like George Boulis, Van McGee, and others, provides new perspectives on the logical structure underlying the paradox. Another area of current interest is the development of paraconsistent logics, logical systems that can tolerate contradictions without exploding or deriving every possible statement. Some researchers have explored whether Russell's paradox might be acceptable in such systems, leading to new approaches to set theory that allow contradictory sets to exist without destroying the entire system. Category theory, a branch of mathematics that focuses on the relationships between mathematical structures rather than the structures themselves, has provided new perspectives on foundational questions raised by Russell's paradox. Category theorists often work with concepts like the category of all categories. That would be problematic in traditional set theory, but they have developed techniques for handling these concepts that avoid paradox. Homotopy type theory, a recent development that combines type theory with ideas from topology, represents another modern approach to foundations that has been influenced by the lessons of Russell's paradox. This approach provides computational foundations for mathematics that are particularly well suited for computer verification of mathematical proofs. Computer science has also generated new interest in Russell's paradox. As researchers develop more sophisticated programming languages and proof assistants, they must grapple with the same issues of self-reference and type consistency that Russell identified. Modern type systems in programming languages like Haskell and Scala use hierarchical approaches that are direct descendants of Russell's original type theory. Research in cognitive science has examined how humans understand and reason about paradoxes like Russell's. These studies provide insights into the psychology of mathematical reasoning and the sources of our logical intuitions. As we near the end of our journey through the world of Russell's paradox, it's worth reflecting on what this century-old discovery can teach us today. The lessons extend far beyond mathematics and logic to broader questions about knowledge, reasoning, and the nature of rational inquiry. First, Russell's paradox teaches us about the importance of intellectual humility. The principle of unrestricted comprehension seemed obviously true to the brilliant mathematicians who first formulated it. The idea that any well-defined property should determine a set appeared to be a fundamental truth about the nature of mathematical objects. Yet this obvious principle led directly to contradiction. This suggests that even our most basic intuitions about logic and mathematics can be flawed. No matter how obvious a principle might seem, it must be tested against the full consequences that follow from it. Mathematical truth is not simply a matter of intuition. It requires careful logical analysis and systematic exploration of implications. Second, the paradox illustrates the creative power of mathematical crisis. When Russell discovered his paradox, it seemed like a disaster for mathematics. Frege's system was destroyed, the foundations of set theory were called into question, and the entire project of mathematical foundations appeared to be in jeopardy. Yet this apparent catastrophe led to some of the most creative and productive work in the history of mathematics. Russell developed type theory. Zermelo created axiomatic set theory. Hilbert launched his formalist program. Brouwer founded intuitionism. Gödel discovered the incompleteness theorems. Each of these developments arose directly or indirectly from attempts to understand and resolve Russell's paradox. Mathematical crises, it turns out, are often mathematical opportunities. When our existing frameworks break down, we're forced to develop new and more sophisticated approaches. The history of mathematics is full of such creative responses to foundational problems. Third, Russell's paradox demonstrates the subtle dangers of self-reference in logical systems. The paradox arises because we allow a set to be defined in terms of a property that the set itself might or might not possess. This creates a self-referential loop that leads to contradiction. Similar self-referential problems arise throughout logic, mathematics, and computer science. Gödel's incompleteness theorems use self-reference to show the limitations of formal systems. The halting problem in computer science involves programs that analyze themselves. Consciousness researchers grapple with the problem of minds trying to understand themselves. Russell's paradox was one of the first clear demonstrations that self-reference must be handled with extreme care in rational systems. The solutions that emerged: type hierarchies, stratification principles, axiomatic restrictions provide templates for managing self-reference in other contexts. Fourth, the paradox illustrates the deep connections between logic, mathematics, language, and philosophy. Russell's paradox began as a technical problem in mathematical logic, but its implications spread throughout philosophy and have influenced fields as diverse as computer science, linguistics, and cognitive science. This interdisciplinary influence reflects the foundational nature of the logical principles involved. Questions about sets, properties, and self-reference are not merely technical mathematical issues. They touch on fundamental questions about the nature of concepts, language, and thought itself. Finally, Russell's paradox teaches us about the provisional nature of mathematical knowledge. The history of the paradox shows how mathematical foundations are better understood as sophisticated constructions that serve particular purposes rather than as absolute bedrock truths. ZFC set theory provides excellent foundations for contemporary mathematics, but we shouldn't think of ZFC as capturing the final truth about the nature of sets. It's an elegant and powerful system that avoids known contradictions and supports the mathematics we want to do. But it's still a human construction, chosen for pragmatic and theoretical reasons. Future developments might lead to different foundational approaches that are more suitable for new mathematical or computational needs. The story of Russell's paradox suggests that mathematical foundations will continue to evolve as our understanding deepens and our needs change. As we conclude our exploration of Russell's paradox, It's important to recognize that the story is far from over. More than a century after Russell's fateful letter to Frege, the paradox continues to influence mathematical research, philosophical inquiry, and practical applications across multiple fields. In pure mathematics, researchers continue to explore alternative foundational systems. Quine's new foundations, long suspected of being inconsistent, was finally proved consistent in 2010 through sophisticated computer-assisted techniques. This achievement has renewed interest in alternative approaches to set theory that might offer advantages over ZFC for certain applications. Category theory continues to provide fresh perspectives on foundational questions, offering structural approaches to mathematics that sidestep some of the issues that led to Russell's paradox. Homotopy-type theory represents a new synthesis that combines computational and geometric insights with traditional logical approaches. In computer science, the lessons of Russell's paradox are built into the foundations of programming language, design, and verification systems. Every time a programmer uses a type system that prevents certain kinds of errors, they're benefiting from insights that trace back to Russell's analysis of self-referential constructions. The paradox also continues to influence philosophical debates about the nature of mathematical objects, the foundations of logic, and the limits of rational inquiry. Contemporary philosophers of mathematics still grapple with questions that Russell's discovery made urgent. Are mathematical objects real? What makes mathematical statements true? How should we understand the relationship between logic and mathematics? Research in cognitive science and psychology examines how humans understand paradoxes and self-referential constructions. This work provides insights into the cognitive foundations of mathematical reasoning and helps explain why paradoxes like Russell's are both puzzling and illuminating. In artificial intelligence and machine learning, researchers must carefully design systems that can reason about themselves without falling into paradoxical contradictions. As AI systems become more sophisticated and autonomous, the lessons about self-reference learned from Russell's paradox become increasingly relevant. Educational researchers continue to study how students learn about paradoxes and foundational issues in mathematics. Russell's paradox serves as a powerful tool for helping students understand the importance of logical precision and the provisional nature of mathematical knowledge. We began this journey with a simple question: does the set of all sets that don't contain themselves contain itself? This innocent-looking question led us through over a century of mathematical development, from Russell's discovery in 1901 to current research in logic, computer science, and philosophy. Russell's paradox proved to be not a dead end, but a doorway. It forced mathematicians to abandon naive assumptions about sets and logic, leading to the development of more sophisticated and powerful foundational systems. It sparked creative responses that enriched multiple fields of inquiry. It demonstrated the subtle complexities involved in self-reference and logical consistency. Most importantly, Russell's paradox embodies mathematics' capacity for self-correction and growth. When faced with a fundamental contradiction at the heart of their subject, mathematicians didn't give up or retreat into skepticism. Instead, they rolled up their sleeves and built better foundations. The story of Russell's paradox is ultimately a story about human intellectual courage and creativity. It's about Frege's dedication to truth, even when it destroyed his life's work. It's about Russell's relentless pursuit of logical clarity. It's about the mathematical community's collective effort to understand and resolve a fundamental crisis. Today, when we use computers whose programming languages embody type systems derived from Russell's work, when we prove theorems in axiomatic systems developed by Zermelo and others, when we grapple with questions of AI safety that involve self-referential systems, we are continuing the intellectual journey that Russell began in that spring of 1901. Russell's paradox reminds us that mathematics is not a static collection of eternal truths, but a living, growing human endeavor. It's a field where apparent disasters can become sources of profound insight, where simple questions can reveal deep complexities, and where the collective human intelligence continues to push against the boundaries of the knowable. The barber may never be able to consistently decide whether to shave himself. But in wrestling with that impossible decision, we've built the logical foundations that underlie much of modern mathematics, computer science, and rational inquiry. Not a bad outcome for a paradox that once seemed to threaten the very possibility of mathematical knowledge. Perhaps that's the deepest lesson of Russell's paradox. Sometimes, the questions that seem most threatening to our understanding are exactly the ones we most need to ask. In embracing paradox, contradiction, and uncertainty, we don't destroy knowledge, we make it stronger, more sophisticated, and more truly our own. And that is the remarkable legacy of a 2-page letter sent on a June day in 1902 from a young English philosopher to an aging German logician, containing a simple question that changed mathematics forever. Remember to like this video if you found it helpful. Subscribe for more.